Okay, so the first experiment on here was trends within groups. And so we're just going to watch this video real quick because it's pretty short. And so in this video, oh, here, let me pause this. So in this video, we have beryllium on the far left, and then it goes magnesium, calcium, strontium. So from left to right, it's the same order that it is top to bottom in the table. Again, from left to right, it goes beryllium, magnesium, calcium, strontium. Okay, and so then what you were supposed to do was order them from most reactive to least reactive. So let's watch that one more time because it's nice and short.
Writing's not that easy, but Grammarly can help.
Thing to click. So you're supposed to order them from most reactive to least reactive. Okay. And so then go ahead and so here, let's watch it one more time. And so what you should see at this point is the strontium, at least in the beginning, is bubbling the hardest, right? And then probably after that, the calcium, because you can see the water level's a little bit lower. And then after that, the magnesium, and lastly, the beryllium, which isn't really doing anything. Now, that being said, as the video goes on, some of you are saying that the magnesium is reacting more, and I can kind of see what you're saying. Look at how high some of those bubbles are getting with the magnesium. And so I don't know exactly why that is. I don't know why the magnesium is reacting more towards the end of the reaction. It should have been the strontium, but if you said magnesium, I'm not going to mark you wrong. That being said, though, for the periodic trend, which is going to be kind of the next thing that we go over, I see that. There we go. For the periodic trend, which is what's going to be the next thing that we go over, what you should see is that as you go down the periodic table, you get more reactive. Remember, that's what we learned last week. So it should have been strontium. It should have gone just in order, right? Strontium's the most reactive, beryllium's the least reactive. If you said magnesium was the most reactive, that's fine. Like I said, I'm not going to mark you down for that. But make sure you understand that for the periodic table, that it gets more reactive as you go down in general. Does anybody have any questions on that before we move on? All right, cool. Let's keep moving. So next we're going to watch these metals. They're reacting with acid. So in the last one, the solution that they were sitting in was just water. This time we're going to watch these metals react with acid, hydrochloric acid to be specific. So first up is calcium. We can skip ahead a little bit to the reaction. Yeah. Okay, so let's just go back a little bit. So we got our calcium metal, and then they're dumping acid into the test tube. And so then you were supposed to record your observations for this. You're supposed to record the observations for all the videos that you watch. You can kind of see what's happening, though. And so this is calcium. Okay, cool. Let's go on to the next one. So that was calcium. Next up is potassium.
Here's the reaction into the beaker of 12 more.
So he's got his acid in there, and then now he's going to add potassium.
Very soft metal. You can see the oxide layer is forming again on the potassium metal. It's that reactive right away with the air. Okay, I'm going to add it to the concentrated hydrochloric acid.
Excellent. All right. And then we got one more video to watch. Let's take a look at the zinc. This is zinc.
When we place the element zinc in hydrochloric acid, it reacts, forming zinc chloride. The reaction also produces bubbles of gaseous hydrogen.
Okay, so go ahead and type it in the chat one more time. Which one do you think was most reactive and which one do you think was least reactive? And again, we're looking at, we're looking at calcium, potassium, and zinc. So Ca, K, and Zn if you want to use the symbols. Which one's most reactive? Which one was least reactive? Go ahead and type it in the chat. Participating in that. Okay, so it seems like we're all pretty much in agreement. Potassium was the most reactive. Zinc was the least reactive. I mean, potassium, you saw the whole thing actually set on fire during the reaction, so that one's got to be the most reactive. And so what you should see, sorry, so to get back to this, I keep getting off task here. So potassium is the most reactive, calcium is the next most reactive, zinc was the least reactive. Well, if you look at those, they're all in the same period, right? And as you go left in that period, they're getting more reactive. So zinc was the least, potassium was the most. So hopefully that, blimp go boom, correct. Okay, so go ahead and type out for number 5, francium, potassium, chromium. Which one do you think is the most reactive? You kids are funny. Yep, people seem to have this down. So for those of you that don't, if you look, so here's francium, potassium, and chromium. I made those ones in red. Well, if you look, chromium and potassium are in the same period. So potassium has to be more reactive because it's to the left. Potassium and francium are in the same group. Francium has to be more reactive because it's okay. So rubidium, zinc, and cesium. Go ahead and rank them. Good. Now I'm going to tell you all. When I wrote this question, I actually made a little typo in there. I actually meant to have that be not zinc but tin. And so you can see tin is right here. It's in the same row as rubidium. And so we know that cesium is the most reactive because it's further down the group than rubidium. And we know that rubidium is more reactive than tin because it's in the same period as tin. You can guess that zinc is less reactive as well because it's also further down and to the left. Or that rubidium is also further down and to the left of it. But I meant to put two groups that are in the same period, not in different periods. But hopefully you could. Okay, let's keep going. So then for experiment 3, that's the one where we're looking at the density trends within a group. Now, experiment 3 for lab 1 and lab 2 together are both really kind of long, so we're not going to watch the whole video. So if you haven't seen these yet, if you want to actually watch this one, just follow the YouTube video that's on the document. I filmed the whole thing happening, but basically we have a mass of silicon. You take the volume before and after, subtract to get the volume of silicon, and then you divide to get the mass. Before you do all this, you have to make a prediction, though. What do you think the density of silicon is going to be? And then you compare your guess with the actual density and see how you did. And so then you'll compare how close was your estimate to the actual density. You do that by calculating the difference. So for number 7, when elements are organized in the periodic table, various trends appear. Describe. I should just say describe one trend that you learned from this lab. So go ahead and type that out. What was one trend that you learned from this lab? Down, left, right. What trend did you learn? There should have been 2 for reactivity and 1 for density. Yep, metals tend to react violently towards the left and the bottom of the periodic table. That's good, Myra. Or Mira, sorry. Farther down the periodic table, the more reactive. Thank you, Elijah. Come on, let's get a few more. We're almost done here, folks. Down means more reactive. Left and down means more reactive. True. Yep, farther. The more up you go, the less reactive it gets. Yep, that's true. That's a good way to say it. Left and down equals most reactive. Good. Okay, good. So it seems like you all get this. How about what was the density trend that you were supposed to get right here? Yeah, the further down you go, the more dense it gets, and that mostly you get that from me telling you. It's not like I actually showed you a lot of data for this, but tin has a density about 7.28. What is the other one? Lead has a density of about 11.34. Yep, up is less dense. That's a good way to say it. What did you guys get for your approximate density of silicon? Did anyone calculate it? Because I haven't actually calculated it yet. I will when I grade it. But what based on our data from the lab, what is that density of silicon? 1.34. So less than 10. Yep. So, and that should make sense, right? It went even further down from what the density of tin was. I'm guessing what's above silicon? Carbon. So if we did the density of carbon, it would probably be even less. All right. And so then number 7, we already did. All right. So let's take a look at the last lab then. That was the metals, nonmetals, and metalloids. So there was 3 elements. And you might have them in a different order on here. That doesn't matter. We've got silicon, which was like a dark gray silver. We've got sulfur, which was like a light green/yellow color. And then we had copper, which is a copper color, right? So like orange, brown, or red. Kind of like a mixture of the 3. Okay, and so then luster. Which one was the shiniest? Which one was the least shiniest? Go ahead and order them in the chat. Which one did you think was the most shiny? Which one was the least shiny? Seems like we're all in agreement on this. Now, it's funny. You guys have almost all said that silicon was the most shiny. And I thought silicon was the most shiny too. My first hour honors class, they almost all said that copper was the most shiny. So it's just funny how different people see things differently. I thought the silicon was the most shiny though. All right, so malleability. So that's how easy it is to like pound things into different shapes. And sort of the opposite of malleability is brittleness. So either when you pound on it, it'll pound into a different shape, or when you pound on it, it'll put on here. All right, so let's do malleability next. Go ahead and rank them. Which one was the most malleable, easiest to pound into different shapes? Which one was the least malleable? Good. So copper, silicon, sulfur. People seem to be agreeing on that. If you remember from the video, like when I tried to take the scupula and pound it into the copper, it didn't really do anything. But I'm sure you could see that copper was already shaped into different shapes. So if you take copper and you heat it up and then you hit it with a hammer, you can pound it into pretty much any shape that you want. The silicon, it took some doing, but when I hit it with the scupula, it eventually broke into pieces. The sulfur, I hardly had to do anything to it. I just pressed on it and it broke in half. So that did not. All right. So then up next is ductility. That's kind of a tongue twister to say. Ductility. Ductility is a measure of how ductile something is. So how easy is it to shape into a wire? So go ahead and rank those ones. Which one do you think would be the easiest to shape into a wire? Yeah. Yep. See some people are already getting that down. Thank you, Mackenzie. Thank you, Joel. Alan, thank you. Evan, Myra, Layla, Keegan. Thank you for participating. Yes. You guys could probably see that the copper was already shaped into a wire in the video, so that one was the easiest. It would have been really difficult to do with the sulfur, right? You remember when I pressed on it with the scupula, it just broke into 2 halves. If I tried to shape that into a wire, it would just crumble into dust. It wouldn't work. Silicon, on the other hand, you could maybe make a wire out of that. I'll tell you one thing though, like hitting on that with the scupula, it basically just like broke into pieces. And so when stuff is breaking into pieces like that, that's a good sign that it's not going to make good wire. Okay, so then up last was conductivity. Go ahead and rank them for conductivity as well. Emojis. Okay. Yep. Copper, silicon, sulfur. Yep. So what you should have saw in the video was when we put the electrodes on copper, it showed a very low number, like 0.01. Now, what we were measuring in there was electrical resistance. So how resistant was that material to electricity flowing through it? So the fact that copper was at like 0.01, that means that it was almost unresistant. It means that the electricity flowed through there very, very easily with almost no resistance. Compare that to the sulfur. When we put that on there, the electrical resistance was 1, which means that it was 100% resistant to electricity flowing through it. No electricity was flowing through the sulfur. So hopefully that makes sense. So then, which one of the elements above was the metal? Metals are shiny, malleable, ductile, and good electrical conductors. Yeah. And copper, I'm assuming you all probably knew that was a metal before this lab. That being said, now you kind of know these are all the things that you need to look for to identify something as a metal. It's got to be shiny, it's got to be malleable, it's got to be ductile, and it's got to be a good electrical conductor, right? Metals are really all 4 of those things. I will say this, there was one other part that I kind of cut out of the lab because it was getting too long, but you sort of saw this at the beginning. Metals react with acid, right? We saw that in lab 1, experiment 2. We showed all those different metals that reacted with acid. So that's another property of metals, is that they react with acid. Good. And so then how can you tell? Well, you should use the evidence from your lab to describe how you can tell that the copper was shiny, malleable, ductile, and a good electrical conductor. So that's how you're going to explain this. And then where is it located on the periodic table? Group and period. Can anybody tell me what's the group and period of copper? Period 4, group 11, period 4. Yep. And so then just to show you, here is copper right here. We can tell it's in group 11 because of that right there, the 11 up above. And then if we follow it over here, we can see that it's the 4th row. So 4th row, 11th column, or period 4, group 11. Okay, good. That's all I think I really have for you today. Hopefully you can identify what the non-metal and metalloid are, and if you're struggling with that, hang after and I'll help you.